So in this video, we're going to talk about beta decay, and beta is the second letter in the Greek alphabet, so this is the way we write it. And beta decay comes in two flavors. There's a beta minus and a beta positive. The beta minus is simply an electron. A beta plus is a positron. These are antiparticles. Let's see if we can write this correctly. Positron. So a positron and an electron have the same mass, they have the opposite charge, and if they meet each other, then they would react to give us energy. Now, the way these come into play with ideas of radioactive decay is probably best given as an example. Let's clear the chalkboard and give our first example. Let's say we have an atom like potassium 40. Now, because we've written the letter K for potassium, we must have 19 protons. So as a little bit of review, this is the Z value. It is the number of protons. So Z is the number of protons that are in the nucleus, and that defines the element. If we had any other number besides 19, then we would not have potassium. We would not be able to write K. So it's somewhat superfluous to write both of these, but we're going to write that subscript here as an accounting measure to help keep track of what's going on. And then potassium 40, up here we have A, the atomic weight. So this is the atomic weight of this particular isotope, and A is equal to P, the number of protons, plus N, the number of neutrons, or we can write this perhaps more correctly as Z plus N, where number of protons is often written as Z. So A is the total amount of particles in the nucleus, and so whatever number we have here, we need to add a number of neutrons to reach that number there. So potassium 40 can decay into calcium 40. And calcium has an atomic number of 20. And this happens by beta decay. A beta particle is emitted from the nucleus. We also have an antineutrino, so this letter nu is for neutrino, and when we put a bar over it, it means that we have an antineutrino. And then there's a little bit of heat energy that's released, and we'll just write that as Q. So here's the equation. Potassium 40 decays into calcium 40 plus a beta particle being emitted, plus a neutrino, and plus a little bit of energy. So what happened in this decay process? We had a neutron turn into a proton. So in the nucleus, we had a bunch of neutrons, and we had some protons. We can draw some protons. We're not going to draw the complete atom here. This is just for purposes of illustration. So if we had potassium 19, we'd have to have 19 protons, etc. No need to do that. So what we're going to illustrate here is this issue of beta decay. You can think of a neutron here as essentially being the sum of a proton plus a beta particle. And if that beta particle is emitted, so let's have a beta particle flying out of that atomic particle there, then this guy is converted into a neutron. The total number of particles here does not change. We still have the same number of particles, the same number of nuclei, so we still have an atomic number of 40. That doesn't change. But by converting a neutron into a proton by emitting this beta particle, the atomic number, the Z value, goes up by 1. So we're showing no change in the atomic weight here, but the atomic number is going up by 1. And then there's the beta particle that's being emitted, and then there's some other stuff going on. A neutrino is emitted and some energy is released at the same time. So that's the gist of idea of one form of beta decay. There is another type of beta decay. Let's erase the chalkboard and give another example. So what about the case of beta where we have a positron? Well, we can have the example of something like fluorine. Fluorine has an atomic number of 9, an atomic weight of 18, and it can decay into oxygen 18, which has an atomic number of 8. Notice that we have something similar here. We're not changing the atomic weight, so the A value stays the same at 18, but here instead of the atomic number going up, as it did in the previous case, it's going down. We have the emission of a positron plus the emission of a neutrino, not an antineutrino, so no bar above there, plus a little bit of thermal energy. But this is the part that we really care about in here. What's going on here? Well, we'll take, again, we're not going to draw all the particles. We'll have a nucleus where we have a bunch of neutrons, and then we'll draw some protons in here, put the protons in as red. So we are, in this case, taking a proton here, and we're thinking of this as a neutron plus a beta particle that gives it this positive charge. And if that that beta particle is emitted, that positron is emitted, then what's left over would be the neutral part of that atom. This is just kind of a simple way, probably an overly simplistic way of thinking about it. But again, we look at the total number of particles, the way we've drawn this cartoon, it doesn't really change. The atomic number isn't changing, but we've lost a proton by converting it into a neutron, and so the atomic number goes down by 1. And so here we show that with the beta particle being emitted there. So this is a case of another kind of beta decay, but this time involving a positron emission. Let's give one last example of beta decay. A very common system in geology is the rubidium decay into strontium. This is very important for age dating. So rubidium 87 can decay into strontium 87, and in this case the atomic number is going to go up by 1. So you can just pause the video for a moment here. What kind of decay process is this? And with the atomic number going up by 1, that would be an example of beta decay. And here we'll just ignore the neutrino or antineutrino and energy part. We have a beta decay where a beta particle is leaving the nucleus and a neutron is converted into a proton. And then just one final example, we can have potassium 40 with an atomic number of 19, and it can decay into argon 40 with an atomic number of 18. And what kind of decay would this be? You can pause for a moment if you'd like to take a look at the numbers and take a guess. Well, this would be positron decay. We can have positron decay where a proton converts into a neutron. This is kind of an interesting case because there's one other kind of decay where we can write equivalently. Let's erase the chalkboard and rewrite this. We can have potassium 40 actually absorb a beta particle that is negative and also give us argon 40 with an atomic number of 18. What we had written on the previous page before we erased the chalkboard is we had potassium 40 decaying into argon 40 with positron decay. These are different kinds of decay schemes. This one is an example of so-called electron capture. So in this case, we have a proton that will absorb a beta particle from probably the K shell, the innermost shell in the atom, and that will convert into neutrons. So that's what will give us this drop in atomic number here. And so in this case, that would be electron capture. Or you could have a proton that is unstable and decays into a neutron plus a beta particle. And it gives you the same result where you have a decrease in the atomic number. We're not changing the total numbers of neutrons and protons in the nucleus. We're just switching out a proton for a neutron. And so the atomic weights, the value for A would remain the same. So these are some examples of so-called beta decay. And we've also tossed in, for good measure, the idea of electron capture. They all involve these so-called beta particles, the beta minus, which is an electron, and the beta plus, which is a positron.